Okay, so there isn't actually a whole lot that's new in this section, because what the book is introducing that's new is using the indefinite integral sign, so just integral of f of x dx for the general antiderivative. I'd introduced that notation back in chapter 4 when we introduced antiderivatives. So a lot of what we're doing in this section is just practicing taking a bunch of antiderivatives, some of them indefinite integrals and some of them definite integrals, so that we can practice with our anti-differentiation skills and get comfortable with the notation. There is a little bit more of an emphasis on what these integrals mean, so I tried to look at that in the first couple of videos. And then I tried to just sort of go through the homework and look for interesting things that showed up that I thought it might be useful to work through an example or two together. Okay. So one of the things is that I think it's just one of the homework problems, an absolute value shows up. So I wanted to talk about how to deal with that. Now, you might know how to deal with that, in which case I would suggest that you pause the video, go and deal with that, and then tune back in and see if you got it right. Okay. In general, anytime I have an absolute value, I'm going to write it piecewise. Okay. So the absolute value of just x is sort of my model here. Okay. The absolute value of x is one of two things. It's either x or the opposite of x. Now, sometimes students balk when they see that because they're like, wait, absolute value can't be negative. I didn't say it was negative. I said it was the opposite of x. And I'm only going to use that rule if x is a negative number. And that way the opposite of a negative number is a positive number. So that, for example, if I take the absolute value of negative 5, I'm going to get the opposite of negative 5, which is positive 5. Okay. And of course, if x is bigger than or equal to 0, the absolute value doesn't change it at all. Okay. So anytime I have any absolute value, I can write my function piecewise. Now what I'm going to do here is I'm going to focus on just that absolute value part. I'm going to say the absolute value of 4 minus 2x is going to be one of two things. It's either going to be 4 minus 2x, or it's going to be the opposite of 4 minus 2x. And of course the rule is determined by the sign of what's inside the absolute value. So this will be if 4 minus 2x is bigger than or equal to 0, and I'll take its opposite if 4 minus 2x is less than 0. Okay. So that's correct, but it leaves a lot of work to be done in figuring out how to do things. Usually when I have a piecewise function, I like my condition that tells me which rule to use to be expressed just in terms of x. So I pretty much want to see when is 4 minus 2x positive and when is it negative. So I'm going to just create a number line for 4 minus 2x. Very much like the way I created number lines for f prime and f double prime when I wanted to know when they were positive and negative. So I'm going to say, well, where would this change signs? It could change sign when 4 minus 2x is 0. That would be when 4 is 2x, which would be when x is 2. And if I plug in a number smaller than 2, like, 0, I would get something positive. And if I plug in something bigger than 2, like 3, I'm going to get something negative. So I can rewrite this to say that I'm going to get 4 minus 2x if we're positive if x is less than or equal to 2, and I'll get the opposite of 4 minus 2x if x is bigger than 2. And you'll notice if I were to plug in bigger than 2. If I were to plug in 2 here, I would get 0. If I were to plug in 2 here, I would get 0. So I could actually include 2 with either rule. Usually I just choose to include it with the simpler rule. So I include it with the one where I'm not taking the opposite. Okay. Well, if I can do that, that means that I can write my integrand here piecewise as well. So I'm going to just call the integrand here f of x. And then I can say f of x is going to be either 1 plus 4 minus 2x, or it's going to be 1 plus the opposite, so minus 4 minus 2x. And that's going to be determined by how I would evaluate this absolute value. I would evaluate it to 4 minus 2x, if x is less than or equal to 2, and I would evaluate it to negative 4 minus 2x if x is greater than 2. Oops, greater than 2. But then I can simplify each of these pieces. So this would just become 5 minus 2x if x is less than or equal to 2. And here I can distribute my negative, so it becomes minus 4 and plus 2x. So that's going to become negative 3 plus 2x if x is bigger than 2. And once again, these rules should agree at 2. If I plug in 2 here, I'm going to get 5 minus 4 is 1. If I plug in 2 here, I'm going to get negative 3 plus 4 is 1. So they do agree at that transition point. Okay, excellent. So now I'm going to be able to take advantage of some rules of integrals to evaluate this piecewise function. I'm integrating from 0 to 4, and 2, which is where the rule changes, is halfway in between. So I'm just going to say, well, the integral from 0 to 4 of f of x dx, which is what I started with, is just the same as the integral from 0 to 2 of f of x dx, plus the integral from 2 to 4 of f of x dx. I can break it up into those two non-overlapping subintervals. Then from 0 to 2, that's going to be where x is less than or equal to 2, so I'm just integrating 5 minus 2x. From 2 to 4, that's going to be where x is bigger than 2. I'm integrating negative 3 plus 2x. And you might say, well, wait a minute, 2 wasn't included in that interval, but it's included here. Okay? But remember, we said this function agreed at 2. So I could have included 2 with that rule. It's also the case that if a function is defined by this formula on every point in the interval except just the one point, even if it were different at 2, I'd still get the same value integrating that. So if the function is defined differently at just a single point, it doesn't affect the value of the integral. But in this case, it's not. This formula does work on the entire interval from 2 to 4. Okay, excellent. So at this point, we've done all of the hard work. The hard work was figuring out how to deal with that absolute value and write things piecewise. Now we just need to integrate. Okay, so I'm going to get 5x minus x squared, and that's evaluated between 2 and 0. Plus here, I'm going to get negative 3x plus x squared, and that's evaluated between 4 and 2. So when I plug in 2, I'm going to get 10 minus 4, minus, when I plug in 0, I just get 0. Plus, when I plug in 4, I'm going to get negative 12 plus 16, minus, when I plug in 2, I'm going to get negative 6 plus 4. All right, so this is going to give me 6, let's see, minus 0, plus 4, minus a negative 2 is going to be plus 2, and that's going to give me 12. Okay, so absolute values I'm just going to deal with piecewise. Now again, this doesn't occur a whole lot in the homework, but it is a really important skill to have going forward. So I'm just going to put another problem with an absolute value up on the board and suggest that you turn off this video, because I'm about to end it. Okay, try to work out that problem, and then we'll look through it together in the next video. Okay, so let's just say I wanted to evaluate from, let's go from 0 to 5 this time. The absolute value of 1 minus x plus 3 dx. So give that one a shot. If you feel comfortable with that and want to just check your answer, feel free to just log back in. I think what I'll do is at the start of the next video, I'll start by just giving you what the answer is. If you felt comfortable with it and don't feel like you need to watch the entire video to work through it, that's fine. But if you didn't get the same answer that I got, then you should probably watch the video and work through it, find out where things went wrong. Okay?